Hello, this is a tutorial on combined stresses under combined loading. So on Friday, where I finish off, is we look at this example, okay, which I did not really quite finish yet. We're going to continue from there. So we're going to view this structure from another axis. Okay. So before I go on, just to recap, the first thing we do is we have to find where is our neutral axis with respect to the element. Okay, so with respect to the element. Then we view it from different orientation. Remember, this is a 3D problem solving in a 2D world, like a piece of paper, so we have to draw 2D. Then you will not be lost. So over here, the position of the neutral axis, which I'm going to do in green. This is the position of the neutral axis. So you can see from here, the 5.029 times 10 to the power 3 is going to generate a rotation. It's generate a rotation by the neutral axis. So that's why this is a torque. Okay, Ty torque. And then we have a shearing stress that's acting on the neutral axis or on the structure. That's 5.029 from here. Okay. Only analyze the arrows, not the cross and dots. That's why we ignore the cross. Then the next view, we view from Y and Z. There's our element H. And then this is the position of neutral axis. And we know that 12,000 is going to induce a axial load, compression, and moment about X. Okay, we're going to generate from 5.0. Why is that so? Because the structure will deform this way. So this is the deformation. So this is due to bending moment. Last view that we're going to look in the XY plane. So the XY plane, when you view this structure, you see it this way. Okay, so this is the structure. Okay, so it's just a different view. So what we have down here is we have the 12,000. Now it's coming down. Okay, so this is our 12,000 Newton. And then we have a cross at 5.09 or 5.029. So we know that with so the position of the neutral axis, and then we're going to sketch out our element H. Okay, element H. So the moment is with respect to the neutral axis. Okay, I repeat again, the moment is with respect to the neutral axis. So from here, so I do apologize, this is moment by rotation by Z. So I'm going to call clockwise to be positive. Now we're not doing static analysis, okay? We're just defining what is positive, what is negative. So moment about Z will be equal to 12,000. Right, 12,000. And we are given that the distance from here to here, from the axis. So we're given the axis from here to here is 0.15. Okay, so to the axis, not to the element. Okay, a lot of students do it to the element, which is not true. To the axis, so 12,000 multiplied by 0.15, so it's 18,000 Newton or 1800 Newton meter. And so this is to the neutral axis. Why to the neutral axis? Because we know that before I go on, we are also going to declare the element H, okay, because the moment is going this way, is going to be stress max compression. Okay, so the structure, if you look at the structure, how it deform, the structure will bend this way. Now, why we take it to the neutral axis? Because you know that stress is equal to m y over I, and m is to the neutral axis. Okay, and the y will determine the element position. That is why you take it to the neutral axis. Okay. Now let's look at the next problem, or next structure. So what you see over here is a structure. This is example number 2. Okay. Example number 2. So the entire structure does not rotate at all. It's locked in. Okay. If it's rotating, there'll be no stress. Okay. So all these are fixed. Nothing is rotating. So for it to be fixed and nothing is rotating, then you see stresses. Okay. So we are going to let P. Okay. For this case, we're going to let P is equal to 60 pound of force. And then we locate where the element is. So this is the element H is of interest. So from here we can determine very quickly that what I'm going to draw now is the position of the neutral axis. Okay, so this is the position of the neutral axis that is of concern. Okay. Okay. So we're going to have two views. Okay, we're going to view this in the XY plane. So this is our XY plane. Okay, so I'm going to sketch. So this is our XY plane. And this is rotation in the Z. So I'm just going to briefly sketch this out. So this is the shaft DB. Okay. So this is my DB. So this is our point D, point B, then the neutral axis, and then over here is our element H. Okay, so this is our element H. And then we have a view. Okay, so let me move point B first. Point B. Sorry. So this is point B. Then we have element. No, we have a vertical section going up. Okay, and then this is our. Then we have a horizontal part. So this is point A. And then we have a load coming down. So from here, excuse me, we know that we have V in the Y direction. So we know that we have Vy will be equal to Vy is equal to 60 pounds coming down. And then we know that we're going to have this is going to generate the 60 pounds is going to generate a moment in the z-axis. So moment in the z-axis. So I'm going to call it clockwise to be positive. Moment in the z-axis will be equal to 60 multiplied by 1 plus 5. Okay, so if you look at over here, so this is 1 plus 5, and h is between d and e minus 2. Right, so this is 60 multiplied by 4, so this will be equal to 240 pound-inch of moment. Okay, so anything else to analyze? Nope. So we look from another view, the YZ. So we're going to look at Y. Okay, we're going to look at Y Z plane now. So this is rotation in the X direction. So what you will see now is you will see a circle. Alright. And then this is the position of your neutral axis. And then you have your element H. And then this thing is this is not to scale, by the way. Okay, my bad. Okay, you have this, and it's coming down on a P. So we have a P coming down here, vertically down, and this is 60 pounds. Okay, so how the neutral axis will deform is going to induce a torque, right? So when it's deformed, the neutral axis will not change, will not bend. So that's why we call it a torque. So Tz in the z-axis, sorry, in the x-axis. What z-axis? Torque in the x-axis will be equal to 60. So the perpendicular distance, we are aware that we have a perpendicular distance that we have right. So what we have over here is we have 60 degrees, and we have a distance from here to here is 8 inch. So the perpendicular distance is 8 sine 60. Okay, so 8 sine 60. So we have 415.69 pound-inch of torque going this rotation. Okay, I'm going to do one more example, and I'll come back and do one more example. Thank you.